right, good morning. So when last we met, we had been talking about testing. And today I want to sort of wrap up with a brief mention of testing, just because a few of you maybe haven't quite completed assignment 2 due today at 9 p.m. And so you might be doing a little bit of testing over the course of the next, 11 hours. So we had talked about various strategies for testing. One thing to emphasize, kind of big takeaways, do use testing, do use a variety of strategies, do use unit testing where you look at little tiny bits, individual functions in your program, do use regression testing where you have a test suite of stuff that you think used to work, and as you make changes to your program, make sure it still works. Do write a bunch of unit tests, possibly before writing your client code. Hopefully that ship has sailed already for you, but things happen. So write unit tests before writing client code, before writing what you are going to be testing, and use testing and unit test design to refine interface specifications. In particular, over the course of the rest semester, we are going to be providing less and less testing code for you, and we're going to be relying on you to test your own code. Now, of course, we will test your code later, but we're not going to tell you how we're going to do that. All right, one kind of interesting thing is to think about what happens post-testing. So you've tested and you're pretty sure your program works. Now what? Well, best practices are to actually leave the testing code intact. So entire test harnesses, assert statements, perhaps even entire functions that exist only in the context of asserts and testing code. So in the real world, what you would actually do is you would keep all of that testing code, and in the unimaginable situation that there are bugs in the code that people find later on, or that people's ideas of what they want from the code change, and you actually have to make changes to the code, you will go back and you will start rerunning all of that testing code as you change your program, perhaps even far into the future. So now your immediate question should be, well, isn't that inefficient? We'll get to efficiency testing and efficiency improvement later in the semester, but as a preview, one of the very first answers to the question of isn't that inefficient is always going to be, well, test it. Don't make assumptions about what is and is not going to be efficient without verifying that that is the thing that is inefficient, that's the thing that is costing you time. So, doesn't testing code slow you down? Well, let's take a look at a simple example that maybe you would have included in your code. So here is, just a piece of code. It looks like there are a couple of nested for loops in there, and there is some sort of assert in there that is verifying array indices. So good practice, to include that kind of assert. So we compile it. There's this flag that we're using here, $O stands for optimize. It tells the compiler, spend a little bit more time during compilation getting a really good, efficient translation from the C language to assembly and then machine language. All right, so we run it, we get 0.385. We run it many times, we see it's pretty clustered around 0.385 seconds. All right, now in the spirit of being an experimentalist, we remove the assert. We recompile the code, rerun the code, redo the experiment, and we get 0.385 plus or minus 0.02 seconds. Wait, so what happened here? Well, it turns out that even though you put this assert in there, the compiler is able to analyze your code and figure out that the way your code is run, that assert will never actually hit. So it is smart enough to look at your loop indices and figure out, hey, this assert is always going to be true. It is never going to be false, and so the compiler is free to optimize it away. And so when you look at the assembly language or machine language code output by the version with the assert and the version without the assert, it turns out they're actually kind of identical because the compiler was so smart. Now, this won't always happen. It could be the case that you run the code and it turns out that it is indeed causing a slowdown with all of those extra asserts. So what you can do instead is you can include this magic _define that the assert macro pays attention to. If you go and you look at the assert.h header file, you will literally see that the definition of the assert macro depends on whether or not this ndebug is defined or not. If it is defined, then the entire assert macro will be _defined to be nothing. And if it is not defined, then the assert macro will be defined to, if the condition is not true, then call, print this thing out, and then call abort, and all that kind of stuff. Okay, so you can actually include this _define in your code, or probably better practice is to include it in your make file as one of the C flags that you include on the GCC 217 command line when you are done with debugging for the time. Okay, so this is nice because you're not actually having to change the code. The code stays exactly the same, but you get back that efficiency from not executing the tests in the asserts. And in general, if you have more complicated testing code, you can use the same trick of using _defines and then _ifdefs or ifndefs in order to enable or disable at compile time blocks of code that are only used for testing. And in fact, you can piggyback on that same ndebug macro. So to enable the testing code, you don't _define it. At this point, make sure if you've kind of been doing things to make clean, recompile everything, or to disable it, you include ndebug among the compiler flags. Again, make clean, rebuild everything. Okay, so testing expensive but necessary. We want to be efficient. We have a lot of tools that were presented in this last lecture that you have at your disposal. Test the code, test the test, leave the testing code intact. Questions on testing? Yeah. Exactly. So the question was, if you're doing step-by-step compilation, at what point do you do the ndebug thing? Well, as we know, if-defs and defines and all that kind of stuff are handled by the preprocessor. So that is the stage that actually pays attention to that macro, and that's the stage at which you want to include ndebug. Questions? All right, so now we are going to shift from testing to a different topic, namely data structures. And this is really going to be kind of an initial introduction to some material that you're going to need for assignment 3. And yes, assignment 3 is coming. Don't worry, it is not due until after the midterm and after fall break, but it is coming. So we're going to kind of tee it off by talking about data structures. Incidentally, this is a good time to mention the midterm. There is a midterm in this class. The midterm is next Thursday, so the Thursday of midterms week. And what we've decided to do, because of the enrollments in this class and because of logistics of getting classrooms and stuff like that, for the midterm we're going to go online. So it's going to be an online exam completely within Gradescope. Hopefully you have used Gradescope before. If not, kind of online platform for turning in assignments, but in this case for taking exams. So you will have a 12-hour block between 10 a.m. and 10 p.m. You must pick 1 hour within that block, unless you have accommodations, in which case make sure we know about them well before. So you will have a 1-hour block to take the exam. Exam is closed book, closed notes. Questions about the C language and questions about the topics we have covered so far. There is going to be a lot of review material. In fact, if you go to next week on the schedule webpage, you can kind of get a preview of all of that. We will kind of officially be making that live over the course of this week. So lots of exams from previous semesters, list of topics on the midterm, so on and so forth. Final exam. There's a final exam in this class, and I am sad to report that my efforts in fighting with the registrar to not make it the very last slot in exams period were futile. So it is an in-person exam, the very last slot of final exams period. I'm sorry, I fought the good fight. The reason we want to make that one in person is to actually make you, write some code and stuff like that. And for that, we're going to get big classroom. We'll handle the logistics. Questions so far on the midterm? Yes. By writing code, I didn't mean writing code on a laptop. I meant like writing code using graphite sticks on dead trees. Yes. More questions? All right, we will do a review session for the final. It'll probably happen next Monday evening. Still kind of converging on the exact time. Right now, leaning towards 8:30 p.m. Depending on when we can get a room, depending on when precepts aren't happening, stuff like that. Question? Yes, yes. There are past year's exams available on the website. There are probably, 8 or 10 of them available. Kind of a random selection of relevant ones, because some are not relevant because we're not covering those topics anymore. Yes?
Will assignment 3 be available before spring break?
Assignment 3 will be available before spring break, kind of after the due date of assignment 2. Easy enough to get started on that. Yes? I would say that for the midterm, kind of last semester is probably a pretty good reference for what it's going to look like, given that I wrote the exam and it was on Gradescope. All right, data structures. Obviously, there's an entire course on data structures that many of you have taken. Obviously, there are many, many more courses on algorithms and data structures that many of you will take. Our goal here is not to cover algorithms and data structures. It is to give you a little bit of an insight into a couple of data structures you're going to need for assignment 3. And to do this from kind of a memory management point of view. So we want to sneak in a couple of little hints and tips on how you deal with memory explicitly when you are implementing these data structures, as opposed to the nice cushy world of Java and COS 226 when a lot of the stuff happens behind your back. So the goals of this lecture are to look at a couple of data structures. You know, think of these as high-level building blocks in code that you write. Basically, every program you write is going to have some non-trivial data structures in it, but that doesn't mean that those data structures aren't themselves, you know, relatively simple if you take modularity into account and really just focus on their implementation. We are going to be looking at data structures that implement the concept of a symbol table. So a symbol table is a device that stores keys and values. For every key, there is exactly one value. And the operations you may want to do are insert a key with its corresponding value, and given a key, retrieve the value from the data structure. And of course, a lot of the other housekeeping operations, such as update a value for a given key, delete the whole data structure, things like that. So, examples. Maybe the key is a string, and the value is an integer. And so you have a symbol table that stores student names and class years. Or maybe baseball players and numbers. Or maybe variable names and their current values in a piece of code or in a compiler. So, of the dozens and dozens of data structures that you could use to implement a symbol table, and out of the, I don't know, 6 or 8 of them that are actually a good idea to use, as opposed to things you go off and analyze the performance of, we're going to really be looking at 2. We're going to be looking at the hash table, because that very often is the preferred data structure. It's reasonably quick, it's reasonably simple. And before that, we're going to be looking at a linked list, because our implementation of the hash table actually uses linked lists. So these are the 2 data structures that we're really going to cover here. So we'll start with linked lists. Hopefully nothing too new for anybody here. The heart of a linked list is the linked list node. In the context of a symbol table, a node contains a key, it contains a value, and it contains a pointer to the next node in the linked list. In addition, it is conventional to have a separate type, perhaps a struct list, that contains just a pointer to the first node in the linked list. And that is really the bare bones implementation of a linked list. You can start getting fancier from here. And for assignment 3, you may or may not need to get fancier from here. So in the case of the symbol table data structure we're looking at, keys are strings and values are ints. And so the representation here is that we have a struct list. The struct list contains a pointer to the first node in the list. This has a key of Gehrig and a value of 4. The next pointer points to the next node. It has a key of Ruth and a value of 3. And the next pointer of this one is null, signifying that you are at the end of the linked list. Please do not forget to set the pointer to null, otherwise you will keep walking and walking and walking and walking and not reach the end of the list. Question? You can make circularly linked lists in C as long as the pointer points backwards. Whether or not this is a good idea, I leave to you and your ability to implement it without going in a loop and keep walking and walking and walking around the list. More questions? All right, one little detail here. We are drawing this as if the string lives in that key field of the node struct. This is a convenient lie. Of course, in reality, that key field is a pointer to a char. This is how we represent strings in C. And so the string itself actually lives somewhere else in memory, and that key field is simply a pointer to its first character. So this is the first kind of implementation detail where the illusion of the linked list, this kind of nice, simple illusion, is a little bit, well, shattered. So this is something where in a different language, maybe you just write, string right there, but in C you actually have to worry about where are the characters of that string actually allocated, and you have to worry about having that pointer to the first character. Accessing a linked list, fairly straightforward code. Let's go through what's happening here. We are creating a struct list called lineup. So the first thing we do is we're going to do something a little weird, something that you normally wouldn't do in your code, just to show that we can. Namely, we are creating one node on the stack. That is, one of the nodes is going to be a local variable. And this is the more common way that you would do this. You would actually allocate that node on the heap. So it is allocated at runtime. So we have a node G, it lives on the stack. We have a node R, it lives on the heap. We are going to set the key value of the G node to Gehrig. So what happens here? Well, the actual characters of the string, the compiler is going to place those in the RO data section. It's going to get a pointer to those, stick them in the key value of the G node. Lineup.first. So lineup is our list data structure. We need, right there, a pointer to the first node. But because we're doing this kind of weird thing, just because we can, we actually need to get the address of the G node in the local stack frame. And we do that using the address of operator. And now we can set the value of that node, and we can set the next field of that node to be this other node that we allocated on the heap, which is probably what you're going to be mostly doing anyway. And here we're using kind of this star notation to dereference a pointer. We're using a dot to look up a field of a struct. And you might recall that there is a shortcut for this, which is the hyphen greater than, also known as the arrow operator. Please do not write a real arrow. It is always hyphen greater than. Okay, so silly example, but it kind of shows you a lot of the techniques that you're going to commonly find in code that manipulates linked lists. Questions on any of this code? So linked lists are the kind of thing that there's a little bit of non-trivial pointer manipulation, but this is another one of these where focus on it, go over it, write the code until you're super, super comfortable with it. Because we really want to get you to the point where you can write linked list code in your sleep and just like not even worry, am I getting these pointer manipulations correct? Because then when you move on to more complicated data structures and you have pointers pointing to pointers and pointers threaded in various complicated ways, you need to have the basics under your belt. All right, hopefully simple enough. So now let's play COS 226 student for a little while and look at performance analysis. Yay. All right, how much time do the basic operations on a linked list take? Well, so creating a linked list, that's no big deal. We create this list data structure. Maybe we initialize the first pointer to be null. That's about it. It takes a constant amount of time. What if we want to add a key value pair into our linked list, but our specification is that we don't need to check for duplicate keys? Well, then there's a very simple algorithm. We add that node, we create a node and add it to the front of the linked list, and we don't care how long the rest of the list is, because we're never going to be walking down it. So it's just creating a node and doing some pointer manipulation. Pretty simple, constant time operation. In reality, most of the time, when you use a symbol table data structure, you're going to want to check for duplicate keys. You don't want duplicate keys. If you insert something with the same key, probably the semantics that you want are that you're updating the value for that key. Again, depends on the application, but this is a very common thing to want to do. And so now here, potentially, you are traversing the entire list. You might get lucky. You might find something with the same key right at the beginning of the list. But you might get unlucky. There might be something with the same key way at the end of the list. Or you might get even more unlucky, and that key isn't in the list already, so you have walked the length of the list, figure out that that key wasn't in the data structure, and now you still need to do an insert. So you might get lucky, probably you won't. And so we say that on average, kind of the expected time here is that this is going to be a linear time operation in the current size of the linked list. So for our purposes, we're going to be calling that slow, not fast. Obviously, you know, those of you who have looked at more complicated algorithms are saying linear is slow. Well, yes, compared to constant, linear is slow. All right, what about search? Let's say you want to do a lookup in this data structure. So we want to traverse the list, looking for the current key. If we find the key, great. If we've reached the end, we haven't found the key, we report we didn't find the key, using whatever convention your code is using. And so we can ask now, let's see, put this up. You can ask, how fast is searching for a key in a linked list? All right. So, you know, let's think again. Are we going to get lucky or are we going to get unlucky? What is the luckiest you can possibly get? You start searching for this key in this list. Oh, look, in that first node in the list, there it is. Or in the first few nodes, there it is. That's getting lucky. Getting unlucky is you look through the entire list and it ain't there. So now you have paid linear time to go through that entire list and not find anything. So is it always going to be fast? No. Is it always going to be slow? No. What happens kind of in the average case? Well, in the average case, it sort of depends on the distribution of keys and distribution of searches. Well, let's say on average you have to walk halfway down the list. So that is still proportional to the length of the list. And so, subject to a lot of caveats, you can have very skewed distributions of inserts and queries, but probably the best answer is that on average you're paying linear time, and so on average this is a slow operation. Okay, so just now to complete our list of algorithms, we said that search on average is kind of going to be slow, and to free a linked list data structure, well, you have to call free on every single node. The free, free open close function that is malloc's friend. We have to call that on every single node, so this is a linear time operation. All right, so linked list, a lot of the algorithms that you care about are actually going to be linear time. They're actually going to be slow. So linked list really is fine if you're doing a symbol table of length, 4 or something like that. But if you're doing a symbol table of length 1,000 or 1,000,000, probably not the data structure you want to be using. Instead, you probably want to use something like a hash table. And so why did we bring up linked lists? Well, because the way we are going to implement a hash table is using linked lists. In fact, a hash table is going to be an array of linked lists. The different entries in the array correspond to different hash values, and everything that hashes to the same value gets inserted into a linked list in that cell of the array. Okay, so there are lots and lots of variants of hash tables. This is the one called hashing with separate chaining, which for some people brings kind of bad flashbacks of 226. So here's the data structure. We have an array. The length of the array is bucket count. In this case, it is fixed at compile time. You could also have this number be determined at runtime, in which case here you would have to take care of allocating and deallocating the array. What is in each element of the array? Well, it is a pointer to a struct binding. So we're going to have a linked list of bindings. Binding is the terminology we're going to be using instead of node here, because we're specializing to the case of a hash table. But it looks like the node of the linked list just as before. It has a char pointer as the key, it has an int as a value, and it has a pointer to the next binding in the list. Okay? So here's kind of what it's going to look like schematically. We have here an array of pointers. Many of these are going to be null. In fact, they're going to start out all being null. Once you start inserting things, you start getting pointers to the bindings. The bindings chain to each other as long as they fall within the same hash bucket. And you get these linked lists here. So now we come to the hash function. The reason a hash table works is because of the hash function. Hash function takes a key and produces a bucket within which that key should live. So the way we're going to define it is that the hash function produces an integer, potentially a big integer, and we're going to use a relatively simple operation, modulo the bucket count, in order to map to a particular bucket. Okay, so let's look at a trace. So we're going to assume bucket count is fairly small, so we can draw it on the slide. So bucket count is 7. And we are going to add the cat in the hat. All right. We run the bash function. Hash function on the word the, on the string the. We get back some random big number. Well, not random, deterministic number. Modulo by 7, we get 1, and so we're going to live in bucket 1. All right, nothing in bucket 1 already, so we create a binding. The key is the value is whatever we specified. Cat. We run the hash function on cat. Modulo 7 is 2. There's nothing living in 2 currently, so we add a new binding. Similarly for in, the hash function returns a value. Modulo 7 gets 5. Buckets of 5, nothing there already. We add in. Now we get to the again. So here, we run the hash function on the. We better get the exact same value we got before when we ran the hash function on the. And in fact, we do. We modulo by 7, we get 1. And now we search the linked list in bucket 1 for binding with that key. So now we actually have to start doing string comparisons. And in fact, we find it. And so we update the value, move on with life. Hat. We run the hash function on hat. We get a number, modulo by 7, we get 2. But now we have a hash chain already, a chain of bindings already in bucket 2. We need to start walking down bucket 2. The first binding we come to has a key of cat. We do a string comparison between cat and hat, and we figure out that they are not the same. We have not found our key. We keep walking down that list, and we discover we have reached the end of the list. Therefore, our key is not in the hash table, and so we add it to that list. Where do we add it? That's kind of an implementation detail. Might be simpler to add it at the front, or if you have walked down this hash chain, you might have a pointer handy to the last binding in that list already, so it might be just as simple to add it to the end. Doesn't matter. All right, so that is the hash table as we're asking you to implement it. Let's look at the operations. Creation, still constant time, no big deal there. Add. Well, we need to run the hash function, mod by bucket count, traverse the bucket list, traverse the list in that bucket to make sure there's no duplicate key, insert the new binding, and how long does all of that take? So, how fast is adding a key to a hash table? Survey says a lot of people answering C. All right, so let's think again. Are you going to get lucky or are you going to get unlucky? If you get lucky, you need to compute the hash function. Well, we'll kind of get back to that, but let's assume that that's pretty fast. So compute the hash function modulo by the number of buckets, and if we got lucky, there's nothing in that bucket. If we got slightly less lucky, there's like one thing in that bucket or two things in that bucket. Okay, so that sounds fast. How can we get unlucky? Well, we get unlucky if that entire linked list is really long, and we have to search through most or all of that linked list in that hash bucket. So how likely is that? Well, if there are a lot of keys that hashed to that bucket, well, they're kind of in trouble. But the point with hash tables is you don't really want it to get to that point. If you're using hash tables correctly, you're managing the number of buckets depending on how many keys you're throwing into that hash table. And so you want to keep the hash chains relatively short. That is the right way to use a hash table. And that makes it very, very unlikely that just by look of the draw, you have a long hash table and you run into this slow performance. So the reason you use hash tables is because, on average, if you're using them correctly, the hash chains are short, and therefore a search operation is fast. It's constant time-ish. So search, usually fast. The one operation that's kind of slow is freeing up everything. Kind of really can't do much with that. You have to go and you have to free everything you allocated. All right, hash table issues. First issue, how many buckets? Well, like I said, if you're using it right, there are a lot of buckets. The number of buckets is kind of on the order of the number of keys you want to put in the hash table. On the other hand, if you're going to have a hash table with 10 keys, you don't want 1,000,000 buckets. That's wasteful. So, like I said, you kind of want it to be the same order of magnitude as the number of keys you're going to have. What about the hash function? The hash function is kind of critical. It really has to disperse the set of keys evenly across the set of buckets. So what is the worst possible hash function? Well, return 17. That sticks everything in the same bucket. Please don't do that. So, there's an entire art and science of creating good hash functions. We're going to give you a simple one, which is a weighted sum of characters in the string. And the weights of the different characters are powers of the same constant. And it's best if that constant is relatively prime against the number of buckets that you have. Consult your friendly neighborhood mathematician for details. So this formula plus some math plus some coding gives you an implementation that looks kind of like this. You're walking through the characters of the string. You are checking for the null. That's when you terminate the loop. And you are multiplying the existing hash value by this multiplier and adding in the next character. So obviously proportional to the length of the string, but assuming that your keys don't get too long, they're bounded, the running time of this is also bounded. Finally, interesting little detail about implementing symbol tables in C. The question of ownership. And this is kind of a, high level of describing really memory management. So let's start by looking at a way of doing this incorrectly. So let's say you're implementing your hash table, you're coding up the add function, adding to the hash table. So, you compute your hash function, you walk down the appropriate list of bindings, blah, 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 blah. You're ready to allocate a new node. So you call malloc with the size of the binding, and now you need to fill in the fields of that binding. And so, most obvious thing in the world, set the key value of the new binding to just be equal to the key that was passed in to the add function. Simple enough. Just moving a pointer really fast, copying a pointer. So now, let's imagine that that's your implementation. You run it in some code. You create a key, you add it to the table. Time passes, and now the calling code modifies the key. So it modifies the characters in memory where that key was stored. But your hash table just has a pointer to that very memory. So now what's the problem here? Effectively, you've changed the key for that binding. And so now your data structure is Swiss cheese. You're never going to be able to find either the old or the new key ever again, because the new key is in the wrong hash bucket and the old key is gone. It got overwritten. And so this is kind of poor practice. So instead, what we're going to suggest is that you protect your keys by making a copy of the keys. So when you create a new binding, instead of just copying the pointer, you create a fresh copy in memory of the actual characters corresponding to the string, and the binding contains a pointer to that copy. So now, the rest of the program can do whatever it wants with the original string, and your data structure is still happy, it is still internally consistent, and it still works. I add one here. If you don't know the answer to that immediately, start looking through previous lectures. We've gone over this very exact bug. Please don't make this bug. And what is missing from this code? Again, something about previous lectures and checking the return from malloc against null. Question here. Sorry? Was your answer check the return value of null, of malloc? Yes, yes. Plus the usual, meaningful variable names, plus the usual comments, all that kind of stuff. Okay, so now considering the same calling code, the binding has its brand new copy of the key, and when the calling code changes the original key, the data structure is still happy. Now, of course, this complicates the freeing operation, because now when you free a binding, you also have to free the copy of the string. So, a few more details. So we now say that the hash table owns its keys. So this is where we get back to the concept of ownership. The hash table now has taken on responsibility for making sure that the keys that it allocated eventually get freed. So summary, linked lists, hash tables, get to know them, get to love them. You're going to be using them in assignment 3.